to Calculus 1. We're still talking about derivatives. And today we're talking about the most important technique, which is called chain rule. And most of the derivatives are taken by using a chain rule. Chain rule is used anytime when you have to take the derivative of a function composition. So if you remember from your pre-calculus days, there was something that looked like this, which was labeled as a function composition when you, let's say, take the function g and you plug that function inside the function f. So if you have, let's say, f of x is equal to x squared minus x plus square root of x plus 1 over x. I just wanted to pile up as many of these as I can. We know from Precalculus 1, hopefully, that we can compute this expression for, let's say, number 4 by plugging in 4 everywhere for each x, and then compute values, and that's going to be equal to some number, right? What's that? 16 minus 4 is 12, plus 2 is 14 and a quarter. There you go, 14 and a quarter. Now, instead of this 4, which is a number that we can use as the input, we can actually plug in the function g of x. So let's say g of x is equal to, I don't know, 2x minus 3. And we can replace that. So now f of g of x is going to be, we replace every single x in this function, we replace it by the function g. So it's going to be 2x minus 3, everything squared, plus 2x minus 3, which is just x, plus square root of 2x minus 3, plus 1 over 2x minus 3. And then you can massage it with algebra to simplify it as much as possible if you care about it. So this is what we have. My question is, for today, what is the derivative of this? All right? How do I take the derivative of function composition? We have two functions there, f and g. You can have 3, 4, 5. We'll go there. But I want to know what is the derivative of this and how to do that one. Sometimes you can avoid it. If you need to find the derivative of, let's say, x minus 1 squared. Well, what you can do in this case is you can FOIL, right? And x squared minus 2x plus 1, and then take the derivative, get 2x minus 2. But what would you do if that exponent was 104? You're not going to FOIL 104 times, I hope, right? So 103 times. So we would like to develop a shortcut method so that we don't have to FOIL, and also something that would, right, allow us to skip on that limit procedure, right, from the beginning of the chapter. So here is the chain rule formula. Chain rule formula says, if you are taking the derivative of a function composition where g of x is plugged into f of x to create function composition, we will take the derivative of the outer function, which is f of x, so f prime, with the g of x still plugged in, and multiply that by the derivative of the inner function, which is g of x. So that's the formula. This is the one that you are remembering, and this is the one that we're going to use. So technically, what's happening behind the curtain, if you're interested in mechanics of this and trying to actually understand, not just memorize the formula and then use it, what's happening here is in this chain rule, you are first taking the derivative of f in respect to g and multiplying that with the derivative of g in respect to x. Now technically, these guys cancel, and you actually end up with the derivative of f in respect to x. And f was in terms of g at some point. So that's actually what's happening in the background. And if you care to know more about it, I'll see you in the office hours, as this is not the honors section. But some of you still might want to explore that. So let's start with simpler examples. For instance, the derivative of sine x squared. The first thing that I used to do, well, I still do it just faster, is analyze the function and see what is the outer function f, what is the inner function g, and then take those derivatives. So as I'm looking at this, as a student, I always used to say to myself, okay, which one is the boss, right? Which one is the boss? The boss is the one on the outside, right? And then the one on the inner side is just running around, and it has to be there, right? So I would say that the outer function is sine x, because that's the one that it's on the inside. And then g is the x squared, because I can definitely replace that x from sine x with x squared, and I would have exactly what I have in the problem. So it appears that I'm supposed to take the derivative of sine x with g still plugged in. So what's the derivative of sine x? Cosine x. But I will write cosine x squared, because it has to be cosine of g of x. And then I will multiply that with the derivative of g, which is 2x, for the result of 2x cosine x squared. And that's where the story ends. You're done. That's the derivative. Now, if this did not make any sense, I can do this problem with a little bit more detail. So same example. I still have this because this cannot be changed. But what I'm going to do now is I'm going to actually do this. I'm going to say the derivative of this should be cosine, find the derivative of sine of g of x. And we know that g of x is x squared. So see, I'm looking for the derivative of g of x. G of x is the argument of sine. So if I take the derivative of sine, I will get the cosine of whatever is in there, and then multiply that by the derivative of this. You just need to plug in g. So I hope this made some sense if the previous one didn't. Technically, the mantra is take the derivative of the outer function and multiply it with the derivative of the inner function. That's what it is. All right? Happy? Marginally happy? Not happy? I'm polling the classroom, 70% not happy. We'll do more examples. Well, stream needs to know what's happening. You're not alone. The square changed the location. What now? What's f? X squared. And what's g? Exactly. So as you replace that x with sine x, you get sine squared x. So now, what's the derivative? The derivative of the outer function is 2 times x, but instead of that I have to write g. And then times the derivative of the inner function, which is cosine x. That's the g prime. And obviously, to be fancy, you will write sine 2x because you know the formula, right? Yes. Yes, it is. Here it is. 2x. This over here, x is x squared, right? Yeah. So if this is x squared, then this is 2x. Think of it as g squared. What's the derivative of g squared? 2g. It's exactly how you should think. This is g squared, and it's going to be derivative of g squared is 2g times g prime. That was g, there's your g prime. It takes some time to get used to these calculations, but once you get the hang of it, you will not be thinking about any of these things, you'll just be flying. Because that's the outer function. I can rewrite this function here, sine squared x, as this. Those are the two. These are the same notation. I mean, sorry, different notation for the same thing. If the square is on x, then it's no longer sine times sine. Now it's sine of x times x. So it's very important where this square is. If it's on the sine, then you have two sines. If it's on x, you have two x's. One side. So that would be our chain rule. Chain rule is used when we have function composition. Find the derivative of square root of 5x plus 3. So what would be the outer function f? X to 1/2 or square root of x, whatever you like. Perfect. So f is square root of x, also known as x to the 1/2, and g is clearly 5x plus 3. So what's the derivative of square root of x? It is 1 over 2 square root of x, but I'm supposed to plug in 5x plus 3 instead of x, and then multiply that by the derivative of g, which is just 5. So the entire thing is 5 over 2 square root of 5x plus 3. I'm going to jump into exercises and just pick few of exercises to work on. Problem number 14. Find the derivative of e to the square root of x. And one more. Something that you're really going to like because we haven't. Like problem 30. You're going to love this one. It's the derivative of cosecant of x squared plus x. See? Wonderful. Okay, no pressure, you have 10 seconds. I'll be right back. I'll take a walk. All right, let's take a look at these together, because we can and we should. The outer function is e to the x, so that's our f, whose derivative is e to the x itself, right? And the inner function g is square root of x, whose derivative is 1 over 2 root x. If you memorize that, if you haven't, then do it. I mean, you can always use limit definition if you prefer that. So now, the derivative of the outer function. So what is this derivative equal to? I have to install a switch. So it's e to the square root of x times 1 over 2 root x for the total of e to the root x divided by 2 root x. So let's take a look at all of the features. This is the derivative of the function f. Remember that the little exponent up there is g. So derivative of e to the x is e to the x. Derivative of e to the g is e to the g. So it's itself in this case. And then we are multiplying that by the derivative of g, which is root x, which is 1 over 2 root x as the derivative. And then we combine them. So this function decomposition is important. Second one, the derivative, the function f is cosecant x, and the function g is x squared plus x. So now, what is the derivative of cosecant? What is the derivative of cosecant function? Very good. Negative cosecant g, negative cotangent, sorry, negative cosecant g cotangent g. So negative cosecant g times cotangent g times the derivative of g, which is, very good. That's it. Yeah, I hope you're not disappointed. That's the answer. Awesome. Did I hear that well? You want spicier problem? Okay, here it comes. What is the derivative of secant x plus tangent x all to the fifth power. What's the outer function? X to the 5. Okay, great. Keep working on it. All right, see you next week. All right, let's take a look at it together. So what's the derivative of the outer function? 5g, which is secant x plus tangent x raised to the 4th power, times the derivative of g. Derivative of secant is? Very good. Plus the derivative of tangent? Great. That's it. Okay. So we got the basic skill out of the way. Can we make this more interesting? Yes. All we need to do is to add elements of product rule and quotient rule in the mix, and all of this becomes more annoying to do. And then we use it later to find the slope of the tangent line, so we can find the tangent line. So all of these problems work together. So let's add product rule and the quotient rule into the mix. So what is the derivative of e to the negative 5x sine 10x? All right. Clearly, we don't have e to the x and sine x, right? We have negative 5x, we have 10x. So both of those will have to obey chain rule when we start taking derivatives of those individual pieces. And these two functions are what? What operation is between them? In between them? Multiplication. So this is a product rule. Very good. So you will do the product rule here, and whenever you have to take the individual derivatives of these pieces, you will have to use chain rule to do so. Good luck. Product rule is the main in this case. Product rule is the main. So you will be working out, copy the first, derivative of the second, plus derivative of the second. Copy the first, no. Copy the second, derivative of the first, thank you. Except you will, every time you have to differentiate, you'll have to change it. You learned it as a formula, but I said you don't have to. So you say whatever you want. Look at that. We're almost done. We have like 1 minute left. And that's 3 hours of that, yeah. So do the product rule, and then within the product rule, you will have the chain rule. All right, let's take a look at this convoluted problem together. This is how we party in mathematics. I know. Ready for product rule? The product rule says, well, let's use u and v. uv prime plus vu prime, right? That's the derivative of uv. So derivative of, I'm going to label this as u and v. So I need to copy u, which is e to the minus 5x, times the derivative of v, which is when I unleash the chain rule. The outer function is sine x, so I have derivative of sine is cosine, so cosine 10x, times the derivative of 10x, which is just 10. Awesome. Plus copy v, which is sine 10x, times the derivative of the u, which is derivative of e to the x is e to the x, so e to the g would be e to the minus 5x, times the derivative of g, in this case, minus 5. So let's have this as u, this is v prime, this is v, and this is u prime. We can simplify this a little bit. We can factor out 5e to the negative 5x. And what's left on the first one is 2 cosine of 10x minus sine of 10x. Now, why do I want to simplify and factor? Because chapter 4 is coming. And in chapter 4, this would be the first step of a problem where you take the derivative and factor it to set it equal to 0 so that you can do the other 90% of a problem. So practice factoring your answer completely as much as you can now, so later it's not an issue, because within a month, that's what we're doing. can't see it? Better? Better, right? Derivative of 3 divided by e raised to the square root of 5x plus 1.
Then you don't stay a few hours to Saturday, Sunday. No, you must do.
All right, let's learn some interesting stuff. First of all, the quotient rule. We're just going to throw that out the window because we don't really need it for this problem. You can suffer through quotient rule if you would like to, but there is really no need. Let's use algebra instead, and then chain rule. And quickly you figure out that actually quotient rule doesn't need to exist at all, but eventually we'll get there. So we're going to start with algebra piece, which says that I can take this E and write it to the negative square root of 5x plus 1. And because this 3 is a constant that you get to rewrite, you don't even need a product rule for this problem. Awesome, right? It's called math on Saturday morning. So now that we battled through that, the derivative would be, we copy the 3, and derivative of e to the x is e to the x, so we copy the whole thing as is. And then we take the derivative of this. The derivative is, well, we have negative 1, which we have to copy. And this is the square root, so another chain rule. Wow. There was a chain rule within a chain rule. All right. Now let's take a look at all of the components of this. I just realized this is the question where I actually have this thing. Don't want to know. I thought you would go on. I forgot that I had it. So, can you solve this problem using quotient rule? Yes. Can. Do you really want to? Hopefully no. But you can. What I'm doing is I'm taking the denominator and writing it up with a negative sign on the exponent, because we know from algebra that when you bring stuff up, the sign on the exponent changes. So that's all I have. And now we are running into a brand new issue, and that is that we have a kind of triple nested function, right? We have a main function, then we have g, and then we have age in between as well, which is the reason why we have 1, 2, 3 pieces to our derivative. What's happening here is when I'm taking the derivative of this, 3 is a constant, you just copy that, don't worry about it. The derivative of e to the g is e to the g. And then we have to take the derivative of g. Now that is, well, we have a negative 1 constant in front, I copy that. And then I have derivative of something like square root of x. Derivative of square root of x is 1 over 2x, so derivative of this is going to be 1 over 2 root that thing. And because this is not x, it's 5x plus 1, the derivative of that also has to be put in a chain. Why is it called a chain rule? Because you add links and make it as long as it's needed to be. Because we have 3 functions that nested there, we have 3 pieces in our derivative. Piece number 1, piece number 2, piece number 3. If you overdo it, you're going to run into a trouble, because derivative of 5 would be 0 and that would kill everything, right? So you can't overdo it. You have to stop exactly where you need to stop. And that is, you ask your question. Questions are, how far do I drill within this function, composition function, right, to get to a single x? How far do I drill? Well, I have this function, I have this function, I have this function. 1, 2, 3. I have 3 functions, therefore there will be 3 pieces in the answer. And there they are. 1, 2, 3. So one more time to explain this, we have a function, and because this is not a function here, there are no x, it's just a constant, 3. I am able to bring this upstairs and make it into a negative exponent, and then this 3 will copy. It would be a completely different story if this 3 was replaced by x minus 1 or sine x or whatever else. In that case, yeah, hello quotient rule, and let's suffer. But in this case, it was just number 3. Number 3 can be also kicked out in front of the derivative if you learned any of those properties of derivatives that we talked about last time. So now you have the function set, and you say the main, I call it the boss, right? The outer function is e to the x. Derivative of e to the x is e to the x itself. That's why it's literally Control-C, Control-V, copy the entire thing. Once you have that, you say, well, what's the derivative of the inner function? And then you realize that that one is consisted of two functions, square root of x and then the mass inside, which means you will need another chain rule. How many chain rules I can put? 17,000 if I want, right? All I need to do is to chain 17,000 functions. It will be quite lengthy, but and time consuming, so I don't do those things. But technically, usually the most you will see, including applications, is going to be up to 2 or 3 functions chained down the line, so that you can have the application. I had earlier, I had a problem that was that is seen very frequently in your physics and engineering courses. This is the motion in physics. That oscillations. That's what it is. So when you take pendulum and you swing it, it's going to swing, 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 and then it's going to die out and eventually going to stop, right? So the graph for something like that, so you take a pendulum and swing it, right? And it's going to go like that. The graph for this looks like that. And the equation for that graph is this one, which means the derivative of that equation gives you what? Velocities along the line, exactly. So there's your physics. How cheap and easy physics is if you know the facts. You just need to show up to the class. Be on a roster, right? Appendix. You know math, everything else, physics, chemistry, is just a joke. Not organic chem, that doesn't fit anyway. You have to memorize stuff for that. That one and anatomy and physiology, like good luck with those courses, right? And don't ask me for help. All right? But I know where the skull is, I know where the, but don't ask for the individual pieces over there, right? Yeah. This much easier. You learn like 5 rules and. All right. How many bones do we have? 206. And they all have names? Why? 206. There's just bones. What are the muscles? And what else would you name? Organs? Yeah, I know there's liver, tissues, structures within the individual organisms. And then it can decompose cells, tissue, organelles. Just. And now you know why I do math, right?
Every individual molecule can be named.
Go on, envy me. Look at this. I have 2 rules and it works. They chased me for like a year to go into organic class. There was a time when they used to have organic chemistry once a year, or Orgo 1, and then Orgo 2 once a year. So one semester Orgo 1, and then because they couldn't find enough students. That was back 6 years ago. And Professor Schroer, every time we see him in class, he said, "You have to sign up for organic chemistry." And he said, "No." No. I looked at the book, there are no equations, there is no sense, it's just memorizing things. No, I know. But you have A in general chemistry, like you and other 5 people, you have to go with organic. General chemistry is a joke, he has equations, they give me units, I don't even have to study. They give you tests and they give you units. If you don't have that, you don't know what the formula is, you just plug stuff in, you're done. I opened the book once.
I don't know why. Mine is more chemistry is more important.
Because you were never taught dimensional analysis, that's why. I had the training in dimensional analysis, I literally just had to show up on physics and chemistry. If you know how to do dimensional analysis, you just need to show up for any kind of science class, because When they give you exams, they give you units. When you see the units, you know the formula. You plug the numbers where they belong, and you're done. That's how it is. The worst grade for me in general chemistry on the exam was the one where I had to guess what the reactions are going to give, right? And then everyone else is screaming on how to balance the equation. For me, like 2 seconds balance, get that stuff out of the way, it's easy, right? And then, so everything, it was just joke, the Lewis structures and those electron shells, and it's like, come on. Takes 2 seconds, you look at it, you know immediately. Well, it requires certain mathematical training before that. But then reactions. I don't care, but you take the purple and you take the yellow and you mix them. And something green that smells bad comes out. Just get it out. Class 1, class 2, I'm done with chemistry. Take both. This is funny. No or no. I'm serious. Let's do more of this, it's fun. Oh, I know what you would like to do. You would like to find one of those tangent lines because you can't wait for that problem to come up. All right. So this is why you need Larson book, okay? Look what they think it's a good function for tangent line. Like, why? Why? Really? Like a double chain rule and a quotient rule, good luck, right? Let's do this one. Tangent line, determine the equations of tangent, just for one of these 2 points. 1, 2, good enough. So problem 78, there's the function and just one tangent line, 1, 2. I will write find the tangent line for function f of x equals x times the square root of 5 minus x squared at the point 1, 2. You got this. Take the derivative, plug 1, you got the slope, you have your y, you have your m, you have your x, find p, you're done. Let's go. 37 seconds. Sehr gut. Yes, this is the product rule. Nice. I realized that when I was in North Carolina, got out at Starbucks and looking across the street is Starbucks. What's going?
don't have that issue of worry about I just hope I'm wrong. Crunching, distraction, I literally about 5 6 hours. But it's fun. Sleep fast, but it's not fun. Yeah, but why? So I don't know where you go, right? Someone tells me 10 hours, I say don't tell me you're wasting my time with football. Because you waste like 4 or 5 hours a day. You spend it unconsciously rolling on the floor, or anyone who's doing it. I know.
I'm gonna write that
I guess they shut off air conditioning because this is not getting cool, right?
I think we're done for the year. And calculus, ain't gonna get any colder in the room either. Yeah, this is somewhere. I don't know. Oh, my God. Yes. This is what that's a derivative. Log x against the. Yeah. Well, I just don't want to get too far. Yeah. No, but it sucks when you do like a bunch of work and then you find out like you messed up on the first step and you could just avoid it. Yeah.
Why are you yawning, man? It's like, it's noon. No yawning. It's a math class. Happy. Let's take a look. First we find the derivative. And this is a product rule, which will involve the chain rule as well. I will just code this one more time. So this is u, this is v. We will have to take the chain rule every time we take the derivative of v. So copy u, which is x, times the derivative. So now what we have is 1 over 2 square root of 5 minus x squared times the derivative of the g, which is the 5 minus x squared. And that would be negative 2x, because the derivative of 5 is 0, and then minus the derivative of x squared is 2x. And then we're done. Plus, copy the second one, which is square root of 5 minus x squared, times the derivative of the first, which is just 1. That's your x there. So that's what we have. Now we can simplify this just a little bit. The 2's will cancel right there. So the shorter version is negative x squared divided by the square root of 5 minus x squared plus square root of 5 minus x squared. So we used the product rule, and chain rule was embedded, right? And we found the derivative. Slope of the tangent line M is the derivative computed at number 1. X is 1. So that's going to be negative 1 divided by square root of 4 plus 4, which is 3.5, 7 halves, if you want to keep it as a fraction. Do what? Oh, calculate. As you can see, I use 1 all the time. So as x is equal to 1, x squared is 1. So 5 minus 1 is 4. Square root of 4 is 2. 4 minus... Oh, wait, that's a 2. This is a 2. If this is a 2, then that's 1.5, which is 3 halves. Yeah, 3 halves. Awesome. So we have 3 halves. So y equals mx plus b. Y is 2. M is 3 halves. X is 1. Plus b. So b is 1 half. Right? So tangent line is y equals 3 half x plus 1 half. This is how standard exam question might look like. You might want to star this one. This is awesome question because you had the product rule, you had the chain rule, you had the basic derivative rules, you had the procedure for the tangent line. So instead of having 50 exam problems, you have one that covers 4 concepts. So this is a really good question for the test. Something similar, obviously, but something along those lines. More examples? No? Break time? And then the next section? And then you will work on chain rule a lot at home? I will just mention one more time, chain rule is going to be the most important derivative technique. Almost every derivative from this class on will be chain rule in some form. Product rule and quotient rule will be rare in comparison to chain rule. And basic derivatives almost non-existent. So you need to practice this a lot. And as I said, the most important integration technique called U substitution is backwards chain rule. So you need to know this in order to perform the other one, which is still in Calc1, 5.5. All right, then I will see you shortly, and we'll resume 3.8.